Hello everyone. My name is Abhishek and I am starting my presentation for this project where for the evolutionary, wherein we were told to write a code in GP or GE implementing a classifier which can build a model and which can test the diabetes dataset and get the accuracy. And somewhere it was mentioned that already 69% accuracy was achieved on the validation, and something around 70% or more than that was already achieved in the test data set. I have tried to build the model and I have tried to get the score, and as you can see at the current time of the recording, I am at the third position with 16, which almost around 70% of the accuracy. And this would be my final submission because I tried all the permutations and combinations, and I could see that I have already, if you see, improved my, like, a couple of times. I had got like a couple of hours back I tried, I got around same like 69.883%, but mostly I would be submitting this result. And I think I am at third last week, and from the starting of this competition I was top 10, except the first week where I wasn't able to put some effort. I'll be walking through the PPTs which I have created, and I would be going through the code after showing the PPT. So I have used GP to build the classifier on the diabetes dataset, as we were given an option whether to use GP or GE. So I have used GP, and so pretty much these are the table contents which I will be covering as part of my presentation. And abstract, intro, background and methodology, data collection, preprocessing, exploratory data analysis, genetic programming framework, evolutionary algorithm overview, initialization, fitness evaluation, selection, and then crossover, mutation, and then conversions and terminations. This would be somewhat like what's the end result, and then some sort of representation of my code, and then what I did for as a part of experimental setup, and the results. Confusion matrix, it won't be there. I thought I would add, but it wasn't making any sense. And then I'll be concluding. So abstract, if you as a part of the project, I applied GP to the diabetes dataset with the objective to building a classifier, and I use a GP to evolve mathematical expressions and evaluate for the predictive accuracy. And methodology is the process involved encoding models as tree structure, evolving them using genetic operator like crossover, mutation, and then selecting the best performing model using selection methods, tournament selections, which I used here. And the outcome is that the final classifier performance was assessed on both training and validation datasets, and then showing effective prediction accuracy. And then I used the trained model on my test dataset and analyzed the accuracy on the test data set. So GP, as we all know, is a type of evolutionary algorithm that evolves the program or models to solve problem. It builds upon the principle of natural selection and genetic operations to evolve solutions. And in the project I have used GP, as I said before, and genetic algorithms have been widely used in machine learning for optimization tasks and to getting the best of all combinations, trying all the combinations and getting the best of accuracy, and getting the optimizing the task by finding all the combinations and the best individual, best witness score. And GP extends GA by evolving programs typically in form of a tree structure. And GP can successfully evolve models that are perform traditional machine modules on certain dataset. And dataset is already we have been provided train and test dataset, and the goal was to predict whether person had diabetes based on the features such as high BP, high cholesterol, and so on. We had around 21 features, and the last and one output as a target one. And I had GP is employed to evolve mathematical models to classify the data. The data consists of 5,000 records. This is the trained data, and I have divided the data test into two parts: 80% for training and 20% for validation. There is the test data CSV, which contains 95,000 records, on which I will be building the output CSV file, and that is being used in final submission score. And pre-processing, standardization. All the features are normalized using standard scalar to ensure consistency in the scale of the feature. Train test split: 80% of data is used for the training and remaining 20% is reserved for the validation. And and the framework we will be using trees to build the operators, and the basic functions using GPs are add, subtraction, multiplication, and the trigonometric functions like sine, cos, etc. And each individual representation, each module is represented as a tree with leaves corresponding to feature, node set operator, and evolutionary operators. Crossover combines two parents to create offspring. Mutation randomly modifies a part of a tree to introduce variability. Evolutionary algorithm overview: we have initialized group of individuals, and fitness, we have calculated fitness evaluation based on a fitness function, and performance on the training set, and we have done the selection and crossover. Mutation, which is nothing but the replacement one, and we have employed a gen half and half method. And fitness evaluation is compiling, we have compiled the program and have calculated the fitness and then predicted the output on training data, and also we have calculated the accuracy, and then we have used the same model on building the test data on the test data to see the accuracy. So here is nothing but the crossover and mutation, and the grammar represent, as you know, that we are representing each individual using a tree structure with functions as internal nodes and feature as a leaf nodes. The functions will be the internal nodes and features are the leaf nodes. The tree represents a mathematical expression which is compiled into a function that can be evaluated on the dataset. Here are my experimental setup. Although I have tried different population size and different combination of population generation, crossover and mutation probability, but this one worked for me in the sense that it gave me the highest probability, highest accuracy for the test data. And these were my results from the latest run, wherein I was able to achieve the fitness function, like the validation percentage of 73%, and then when I used it to on my test data, I was getting accuracy of around 70%, almost 70%. And so using GP, I have successfully evolved models for predicting diabetes in the dataset, and the model improved over generation and achieved high validation accuracy. I'll be showing my code, how my model improved over generation, how it achieved validation accuracy. So I'll be just going back to my code, and if you see here, so as usual, I have referred the GitHub repositories which is shared by Connor in the starting, and I have tried to understand all the codes here, and I find out that multiple run could be suitable here, but again I had to run it by setting different parameters for 3 or 5 runs. So I did it like one by one, because at the end it's only one single submission sheet was needed, so I did not really felt it that I should be using multiple run in a single file. So as usual, I have installed the DEAP, which is used for the genetic algorithms in Python, and then I have given some of the protected functions to make sure that my code doesn't breaks, or the operators while building the complex tree structure, they don't break in. So I have used protected sine, cos, safe squares, protected expression negations, and all the other methods. Not all are used here, but I have just added it because I was using all those methods at any point at particular time. And the trend, so here are the imports like numpy and from DEAP I have used base, creator, tool, GP, and algorithm. This GP is the one which is only required when we are using GP. It's not required in other part, but pretty much all these things are required for all most of the algorithms. I have used operators, random, and then scalar to fit my model and scale it. Accuracy score from the scikit-learn metrics, and then train test split to split the training data and testing validation data. Pandas to read the file, and then for plotting we have used matplotlib. So we started by importing the train CSV and then segregating the data into features and target. In X train we have features, and Y train full we have the train data, like the target data, and we have normalized the feature set and then transformed our scalar and transform the X train full, which is nothing but the features, and then we have split the training data using the test size of 0.2, which is nothing but the 80-20% rule, wherein 80% will be the training data and 20% will be the validation data. Then I have built the fitness and individuals, wherein I have initialized a fitness max one because we are looking for maximum fitness of each individual. Then I have built the individual using the fitness max, and then I have started building the tree, which is I created a primary set with this main and having the input of 21, which is nothing but the xtrain.shape. This would be 21. I have added the operators: addition, subtraction, multiplication, negations, and sine, cos, tan. And these are the ephemeral constants and the leaf nodes kind of a thing, terminals. And these are pretty much, I try to rename it. It's not that much necessary, but I have added it to just keep my code neat and clean. And then I have built and register the expressions: gp.gen half and full of, and minimum 1 and maximum 2. And again then I have used the individual to register inside the toolbox. Toolbox is like a container for different individuals which will be a part of a population. And then I have built a list of individuals in the population, then use the compile. I have registered a compile to execute the fitness functions, and then each individuals are evaluated based on this function, this one. And then I got a predictions from the functions in the range of train starting from 0, like a kind of a whatever data we have split in the top. And then I have used the selection method as a tournament with tournament size 3. And then I have used GP mutation, and then I have used 1 point crossover, and then I have restricted my tree to grow not more than 17 like the levels. And these are my parameters as I said before. And I have registered this statistic as well: average, standard, minimum, and maximum. And then I ran my algorithm from first generation to the last generation, and calculating the average fitness score for each generation, average fitness, minimum fitness, maximum fitness for each generation, and adding them into the one particular variable gen fitness. And then once I have completed my run, I have tried to plot the graph of fitness score versus generation. And I got the fitness individual from the training datasets, like the models which I got the fitness individual based on the best of best individuals which I got from this training over the 100 generations. And then I had used that same fitness function to again run the toolbox on, if you see here, to again run the toolbox on the best using the best individual, but this time I will be running this on this data, like the after transforming this data. So the best function, I have used the validation, prediction, and the accuracy score, And then I have used the test data. If you see here, I have used the scalar transform test data, and then again I'm using the best function, this one which we got from the training model, and then we are using the witness functions and in the returning the predictions for the test data. And then once after the getting the predictions, we are storing these predictions in a form of a CSV file using the output as one of the second column and index as the first column, and then creating a file. If you see in the code, we are starting from 70% maximum fitness for accuracy, and then it goes on till increases till 72, then 73, 74%, and then at the end it will be around 90, it will be 75, and from 90 onwards, I think more than 94 onwards, it becomes 76. This all. So that is what the whole code, and that's how my code converges to 76%. Although I was able to get a 76% accuracy, but I tried to increase more generation, but I couldn't get a more optimal result. So with all multiple trials, I got the validation accuracy 73. I have also got a different accurate validation accuracy more than 73, but while uploading my file, I was on the Kaggle, I was not getting the best result. So I think there is some relation wherein if I'm trying to get more accuracy in the validation, so it's overfitting and on the training data sets, and it's not accurately giving results for the test data set. So I realized this validation accuracy is little bit low. I'm getting a fairer result, a better result on the test data. So here is that one, and if you see here my all the previous submissions, I have got something around, like initially I got 67, and I tried to improve my code, and then I end up getting 69 here, and then this was 69, 967. This is the best score. And yeah, this is pretty much my code. I would be submitting report as well in PDF format for this code, and this video I'll be uploading on the YouTube, and I'll share in the link. Yeah, thank you.